Today's lecture is about Bernoulli's equation. So we'll be doing Bernoulli's equation, which is a part of fluid dynamics. You should have watched equation of continuity before this. So Bernoulli's equation is an equation which is based on energy conservation. It states that sum of energy, which can be divided into three types, is constant throughout the fluid. The three types are pressure head and kinetic head and potential head. So throughout the fluid, some of these three heads will be constant. If the two heads are increasing, then the third has to decrease. Or we can say if two are decreasing, the third has to increase. So there are few assumptions in the derivation of Bernoulli's equation. One is that the fluid flow must be steady. Steady flow is a flow in which velocity depends on the location of the point, not on the particle which is coming at that point. Okay, so velocity of the fluid particle must be a function of location and not of time. Means every particle of fluid when it is coming, let's say at this point, must have the same velocity. Okay, similarly, every point which is coming at this point in space must have a particular velocity. Okay, so and the second assumption is fluid is incompressible, and the third is no losses due to viscosity. Viscosity is the property, friction-like property in fluids. So work done by these, we will consider these are the two phases. uh, this pressure at this phase is P2 and at this phase is P1. So the forces will be P1A1 and P2A2. This cross section will move by this amount. Okay, this is the initial line of the cross section. Look at the diagram very carefully. This is the initial line. The cross section has moved towards right, and this cross section has also moved towards right in a small time dt by an amount v1 dt, and this has moved by an amount v2 dt, as v2 is the speed at this point and v1 is the speed at this point. Okay, so we can say the work done by this pressure and the force of pressure and the force of mg is nothing but change in kinetic energy. So we can say work done by this will be positive and by this force will be negative force into displacement, and the work done by this mg will be negative as mg is acting in downward direction, and the mass in these two in between these two cross sections must be equal, as this has moved this and this has moved to this place. So we can say the mass has increased its height by an amount h, so the work done by gravity will be negative, and which will be equal to half into mass of this portion into change in its speeds square of them. So change in kinetic energy, and we get the net work done by all the forces. To find dm, we can use volume, area into distance, area into width, volume into density. These two areas or these two volumes will be equal, so just by replacing density, uh, this is the equation of continuity. Also we can replace the value of dm in these above equation, and we'll get the value as p1 plus rho g h1 plus half rho v1 square is equal to p2 plus h2 rho g plus half rho v2 square. This is the sum of energy per unit volume, which is again pressure energy, potential energy, and kinetic energy heads. These are the energy per unit volume. So at point 1, their sum is equal to the sum at point 2. This is what we call conservation of energy and Bernoulli's equation. Another important theorem in fluid dynamics is Torricelli theorem or velocity of a flux. It is the velocity with which the fluid comes out from a container when a hole is made at a depth h. So we have taken just 2 points inside and outside. This is inside the containers, so pressure at this point will be different. This is outside the container, so pressure at point 2 will be P ATM, whereas at point 1 will be P ATM plus H1 H rho G. The cross section is capital A, the cross section of hole is small a, so we'll apply equation of continuity. Just have a look at that. And Bernoulli's equation at point 1 and 2, their heights are same, so we can neglect that height potential energy factor. So we can get this relation V2 as under root 2 GH divided by this. And if the hole is small, this ratio tends to 0, so V2 will be under root 2 GH simply. This is an important result, should be memorized very carefully. One of the most famous case of velocity of a flux in which there are two holes which are made, one at a depth below h, at a depth h below the surface of water, and another is at a height h above the bottom, and they will be having the same range. So look how velocity of a flux from v1 will be this, and time to fall will be, it has to fall by an amount h minus h. This water has to fall by an amount h minus h. So capital H is the height, total height of the water from base. So half gt square, using the equation S is equal to ut plus half at square. Uy is 0. It is moving horizontally initially. So time will come out to be this. And range will be, this is the range, will be this. Similarly, for point 2, V2 will be this, as the height from the top is capital H minus h. Velocity of a flux formula will give this height, this velocity. T2 will be this, and this distance, range, will come out to be same as in case 1. So for maximum range, this should be maximum, as the range is made up of the product of h and capital H minus h. So the product will be maximum when small h will be h by 2. So to have maximum range, we should make a hole at the midpoint, and maximum range comes out to be capital H. Just by plugging the value of small h as h by 2 in this formula, we'll get the result. So one more important thing to be noticed is reaction force. This is the result for reaction force. As the fluid is moving in forward direction, it applies a reaction force in backward direction, and if the friction is not sufficient, the container may slip. So if friction is less than this force, then this container will move in backward direction. Another important setup is a siphon. Siphon is just a pipe. You must have done this experiment to empty a syntax or a container which is at a height, and just throw a pipe in that and suck it from the other side, and once the water start coming, it will continue to move in without any motor or pump. So we have to find the velocity at point C. These are the height from the water level. So by applying Bernoulli equation at A, we can get at A and C. At point A, the pressure will be PATM plus H1 rho G. This is the base level, so the height of this point is minus h. Similarly, at point A is at the broader cross section, so we can assume that the velocity at this point is almost 0. So we have neglected that velocity. Similarly, For point C, pressure is P atm as the water is in atmosphere. So half rho V square and minus H3 rho G. So from this we can get the value of V as this. In the next part we have to find PB, pressure at this point, and the maximum value of H, which we can take this pipe from this point. So even then the flow continues. So for that, just apply Bernoulli equation at C and B. We'll get PV plus half rho V square, as the fluid will be moving with the same velocity throughout the pipe. So velocity at B and C will be same, and just the height of point B is plus H2 as it is above our base level. So from this equation we get PV is equal to P atm minus this. Okay, one important thing to be noticed that PV can never be negative. Okay, as H2 increases, there's a tendency for PB to become negative. So for H max, PV has to be 0. So we can replace PB as 0 to get the value of H max as this. In the next example, it is explained how an aeroplane flies with the help of Bernoulli's equation. So what happened in an aeroplane, the shape of the wings are made such that the air moving from upward will be moving with the higher velocity, and the air which is moving from the bottom of the wing will have a lower velocity. We have just taken a few random values as 300 meter per second and 100 meter per second. The span of wings is 100 meters square, and the density of air is 10 to the power minus 2 kg per meter cube. These are just random values to find the answer. Again, we have to find the thrust. So where the velocity is more, kinetic head will be more, so potential pressure head has to be less. Similarly, at the bottom, kinetic head is less, so pressure head will be more. P1 will be more. Using by Bernoulli's equation, assuming the height difference between these 2 points is very small, so neglecting them, we can find the pressure difference as this, and we get pressure difference as this when multiplied by area, which is 100. So we can get I think I made some calculation mistake. This is just the pressure difference when multiplied by 100 will give you the force. Okay, thank you.